In this video, I'll talk about sampling variation. This is a quite short video, with an introduction to the other videos in this series. So let's say we calculate a average or a standard deviation from a sample. It's really important that we distinguish between sample values and population values. Population values or true values are the average in the population, like the real average. A sample statistic is just something that we calculate from our limited sample of that population. Right? Those are not the same thing. Let's say if we have the world, all kinds of people in here, right? Let's say these are all people. Yeah. And we take a sample, maybe we sample these and we get an average of 15. Maybe the true average, which we then call mu, was more like 16. We just happened to sample some people that were a bit below that. This is really important. So we distinguish between sample statistics and population values. And notation-wise, we use different notation to indicate them. But so usually, actually not always, but usually we use Roman letters to indicate sample statistics and Greek letters to indicate the population values. I think the one exception mainly is that we're going to use the B letter rather than beta for the population value of a regression coefficient. Actually, I like beta better, but the textbook does B. So that's a bit of the exception here, where we use the B hat for the estimated value. Right, this notation you'll see a lot, this hat. A hat on top of a symbol usually means it's estimated from data, so it's a sample value rather than the real value. So sample statistics are estimates of the population value. The sample mean is an estimate of the true mean. The sample standard deviation is an estimate of the true standard deviation. We don't know the variance, the variation in the real world, we just can only estimate it. Then there's variability in these estimates. We're not gonna get the same thing every time. And that's really, 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 really important to understand. Like you're not gonna get the same average in different samples. Let's say if I have a course with 7 tutorial groups, and I'm going to measure the height, the average height in each of these tutorial groups, I'm gonna get something different. Right? And overall the tutorial groups, there is a population value, there's an average height. We're not gonna get the same value every time. Generally, our hypotheses are on this level. We want to say something about the population level, not about the sample statistic. Say generally, because yeah, you could think of situations where you're just really interested only in the sample. For example, let's say your sample is the entire university of grades and you want to look at that. Then you don't need statistics anymore, right? Because you have all the information. In general, we collect a sample to generalize to the population. And to do that, we need inferential statistics to draw conclusions. So we need to use statistics to do inference, to try to infer something on the population level based on our sample statistics. Right, so examples of hypothesis we might be interested in is, for example, the hypothesis that one mean in group 1 is larger than the mean in group 2. Right, so let's say we have a treatment condition and a control condition. We give some group we give treatment, some group we don't give treatment. And do the people in the treatment condition get a higher level of happiness than the people in the control condition? We're not interested per se in the sample, we're interested in generalizing to the entire population that we get the treatment. And of course, you're never going to get the same mean in two samples. Impossible. Well, pretty much impossible. Like it can happen very rarely, of course. So you always get some differences, but the point is, yeah, is the difference actually in line with like an actual true difference in the real world, or is it just by chance? The correlation between two variables is positive. The first regression coefficient is different from 0, etc. Like all these hypotheses are at the population level. That are defined on population values. Okay, so let's look at our Galton board again. This one that I showed in the other video, right? So it has a real distribution, a true theoretical distribution. We can calculate that. That's the binomial distribution. It's all these, or the other way around, like this. It's because these are binomial chances. Oh, actually I screwed it now. We like +1, +1, +1, etc. There's a maximum amount of bits you can go in. and number of correct responses basically going to the right according to the left. That's the binomial distribution. And we can actually approximate it pretty well with the normal distribution as well. We know that, but every time we run this Galton board, we get something slightly different than that. So let's say here I had only a limited number of balls, and I drew some samples, which I did in R in the computer. You get something that's not particularly exactly this shape, right? It's a bit different every time. Here's a bit like this, a little bit different every time. The mean that you calculate is different. Right. It's not the exact mean of 7, it's something around it. It's very close, there's something around it. Standard deviation too, it's something around it. It has some distribution around this true standard deviation. One thing that's really cool here, in this case, is the Central Limit Theorem. And that means the sampling distribution of a sum or mean of independent variables is centered around the true value. Now, that's interesting because often in psychology, we have a mean and sum of independent values. Namely, we have independent people. And we want to see if the group average of one group is different from the group average of another group. Right, so we have one group, let's say treatment condition, 50 people. You sum all their values divided by 50 to get the average. That is a sum of independent values. Right, and then divided by something that doesn't matter. So this applies to that situation. That's why we're so interested in this central limit theorem. So the sampling distribution of a sum of independent values is centered around the true population. So that's interesting here. What happens here is basically the number of balls. So here we have 5, 10, 25. So it's centered around the true population value. So this is the distribution the sum score takes. Right? So the sum of all these, or the average of all these values. Okay, so we throw 100 balls. What's the average bin they land in? Right, they should land around 7 on average. Right, so what's the average bin they land in? It gets narrower and narrower. It takes a shape of this normal distribution and it gets more narrow. So the mean doesn't change, but it also has a standard deviation, which we call then standard error. That becomes narrower, right? Which is nice, and we can use this to do inference, right? So we can see, okay, with this, we know that this distribution should have this mean and this standard deviation. We can calculate that with the binomial distribution, right? We have theory for that, we have math. And let's say we do this Galton board and we compute for all these balls of the average bins they land in, right? So 1, 2, etc. This is 7. The average bin that they land in. And let's say we suddenly get an average of 8.5, for example. Yeah, 8.5. Now, that can happen here, but it would be very unlikely to happen if you have 100 balls. So if you have 100 balls, then we need, okay, that's just super unlikely. Then this distribution is just actually not correct, because it's not describing where the ball can land. That can be the case, and we have a significant difference, basically. Yeah. That's nice, but often we do not know mu or sigma. We don't know this mean or the standard deviation. And that's a bit of a problem. We don't know the standard deviation, we don't know the standard error. So the standard error is the standard deviation of the distribution of the mean score. Yeah. It gets narrower the higher the sample size, because it gets more precise. This is the distribution of the mean score. We don't know these. Now, often for mu, we don't actually need to know it. We just want to test it's not 0 or it's not something else. Like in this case, we test for 7, for example. Right? But this one is a bit problematic. We don't know it. For this reason, we need to estimate these as well from data, and we need some more advanced inference statistics. All right, that's it for this video.